Okay, antiderivative. A function capital F of x is called an antiderivative of little x of x if, when you find the derivative of the capital, you get the f of x. Let me put example to understand. Example. Suppose que f of x is equal x squared. Then capital F of x is equal 1/3 x cubed. Let me prove that. So you differentiate this. These three go to the front, and you subtract 3 minus 1. 3 divided by 3 is 1. This is x to the second, and we come back to the beginning. In general, when you find the antiderivative, actually the antiderivative of f of x is capital F is 1/3 x cubed plus 1 arbitrary constant. Because you know the derivative of the constant is 0. Entonces actually the antiderivative is not one function, it's a family of the function with a different arbitrary constant. Okay. By definition, the antiderivative is a function capital F. Okay, when you find the first derivative, the answer is the original function. Okay, one symbolic way to represent this idea is using this new notation. This symbol okay. This symbol is the integral symbol. It looks like a one S, one fancy S, long S. You put a function inside, and you finish always using dx. Dx working like a parenthesis, because when you open this operator, it's like you open parenthesis, you copy something here. Finally, you close the parenthesis, and the way to close the parenthesis in this notation is using dx. So dx is like this parenthesis, and this integral symbol is the first parenthesis. Okay, now okay, let me see the power rule of the antiderivative. Suppose x to the n power dx. The formula is n, you increase it, plus 1 divided by n plus 1, plus a constant c. So in our previous example, antiderivative x squared dx, increasing the exponent, now divided by the same number, plus c. This formula is valid only for the m is different to -1. Si es -1, let's see what happens. But it's obvious that it doesn't work because -1 here plus 1 is 0, division by 0 is impossible. So we have some particular example. For example, suppose integral only dx. Well, you can interpretation that the function is 1, and 1 is x to the 0 dx. Entonces x to the 0 plus 1 divided by 1 plus c. The answer is x plus c. So everyone memorize que integral dx alone is x plus c, antiderivative. This is the called antiderivative of integral, indefinite integral. It's the same. Antiderivative is synonymous to say indefinite integral. Okay, another important case is when there is suppose que the exponent is -1, it's special. is integral x to the minus 1 dx. Este es integral dx over x, reciprocal, negative exponent. Entonces dices, what the function whose derivative is 1 over x, es natural logarithm, pero natural logarithm absolute value x plus c. Why absolute value? Well, let me try to explain. It's a little bit complicated. Suppose this new function, que es logarithm absolute value x, is equal logarithm x if x is positive, and logarithm of negative x if x is negative. When you differentiate this, let's see what happens. I don't know. Derivative this. So derivative, see here. Derivative of this. Natural logarithm of absolute value x. You consider like a piecewise function. Derivative logarithm is 1 over x. If x is positive. Derivative natural logarithm of negative is 1 over negative x multiplication, chain rule, the derivative is negative 1. A negative divided by negative is positive. Do you see it's the same function regardless if it's positive or negative? Therefore, the antiderivative of the function 1 over x is natural logarithm of absolute value x, que es different to the absolute value. So absolute value, o sea, logaritmo de x is a function like that, logaritmo x. Pero logaritmo absolute value x is different, it's like that. Two branch. This is the function logarithm absolute value x, and the reason is clear. This is the proof. Let's practice problem about antiderivative now.